All right, so 3.4a, velocity and other rates of change. So we've learned extensively about what the derivative is. We know that the derivative represents average rate of change. And we know the formal definition of the derivative is the one listed here, the limit formula. Rates of change are seen in applications in which derivatives as functions are used in representation of rates of change, which represents the change in the world around us. It is natural to think of change as change with respect to time, but other variables can be treated the same way. For example, a physician may want to know how change in dosage affects the body's response to a drug. An economist may want to study how the cost of producing steel varies with the number of tons produced. Okay. All right now? Oh, goodness gracious. Here you go. Thank you. Okay. When we say rate of change, we mean instantaneous rate of change. So if they ever want you to find average rate of change or average velocity, they're going to have to indicate by saying the word average. If they say rate of change in general, they mean instantaneous, which is the derivative. So please make sure that you note the difference between the two, because from the past, we've always indicated which type of rate of change we're talking about. So you assume instantaneous is basically the moral here. Okay, so find the rate of change of the area of a circle with respect to its radius. So in order to come up with the rate of change for this, we need to at least identify what that formula is to begin with, right? So what would be the formula for area of a circle?
Pi r squared.
Pi r squared, very good. So that's area of a circle. So now we're going to take the derivative of that with respect to r to find the average rate of change of area. So a prime is equal to, what would be the derivative of this equation with respect to r?
0 or 2r?
2 pi r, right?
But wait, but how does the pi still stay?
The pi is a constant,
Yeah.
like anything else.
Oh, wait, catch the r. Okay.
Yeah. The pi is like me saying, this is like me saying 3r squared. It's just the constant in the front. It doesn't affect the derivative whatsoever. Whatever you take as the new constant, which comes from the derivative, just gets multiplied by it. And of course, the exponent always gets reduced by 1 when you take the derivative, right? So area, the rate of change of area can be represented by 2 pi r, but 2 pi r also represents something else in math. It represents the what of a circle? You did circumference, good. Because circumference is pi times diameter, which is the same thing as pi times 2 times the radius, right? So the average rate of change, or the rate of change of area of a circle, is the same thing as its circumference. So then it says evaluate the rate of change at r equals 2 and r equals 3. So let's do r equals 2. We're just going to plug in for r, which gives me 4 pi, right? Which is approximately 12. Well, we can do a better approximation. Let's see. Pi in the calculator, pi times 4, that's approximately 13. And then we're going to also plug in 3. So that would be 6 pi, which is approximately 19. Because pi is a little over 3, right? So those would be our approximate rates of change when the radius is 2 and when the radius is 3. Now if we look at the graphical representation of this, I'll try to zoom in. At 2, does it look like we're at approximately 13?
Yeah.
Yeah. And at 3, we're at approximately, well, we're a little above, but about 20 or 19, right? So you can see that the graph, when we graph the radius with respect to the area, it's approximately the same as the calculated rate of change, okay? And then lastly, it says here, if r is measured in inches and a is measured in square inches, what would be the appropriate units for the derivative of area with respect to the radius? So this, you treat it like division, okay? So area is inches squared, and radius is in inches. What would be inches squared divided by inches? It would just be inches, right? So the appropriate units for the derivative would be inches. So any questions about that? All right. So let's go ahead and look at our formulas. So this right here is going to be like your formula sheet, quote unquote. You're going to use this pretty heavily through this section, even when you go into section point, B, C, and D, which there's going to be. So distance is basically your position. The derivative of your distance is the velocity, and the derivative of that is the acceleration. So you're basically just taking the derivative once, and then you're taking the derivative twice to get the acceleration. So position is often written as x of t or s of t. It indicates location. It can be horizontal. It could be vertical distance. Can be many different things. Displacement is how far we've traveled from where we started. We can find the displacement by doing the final position minus the initial position. The average velocity, if they want this, they have to specify the word average, okay? That's the displacement over the travel time. That's essentially the slope, okay, between 2 points. That's really what it is. So displacement over travel time. Any other type of velocity, we take the derivative of the original function, the position function. Speed is the absolute value of the velocity. Why would speed be the absolute value of velocity? Anyone know?
Negative speed is still speed. Like
Yeah,
it
so
should
basically velocity is essentially speed with direction, right? So if we take the absolute value of the velocity, we just have the speed. So velocity is just speed with direction. If velocity is negative, it's just indicating you're going either down or to the left, depending on if we're talking about horizontal or vertical distance. And then acceleration is the derivative of velocity, or the second derivative of position. And then jerk is the third derivative. So it just depends how many times you have to take the derivative, depending on what they're asking for.
Why would you need the third derivative?
The jerk?
Yeah.
We don't use it that much. It's more something that you have to use it in higher math, but we use mostly acceleration. All right, so an object is moving along a horizontal line with the position function. So in this case, this is horizontal distance. So when we talk about negative, that means we're going to the left. So find the velocity of the function. If they don't specify average velocity, to find the velocity, you take the derivative of the position function. So what would be the derivative of this position function?
2t minus 2.
Good. Then it wants you to find the velocity at 4 seconds. So what are we going to do?
Plug in 4 for t.
Plug in 4 for t. So that's going to give you 6. And since they didn't give us units, you can just say units per second. That happens a lot in math. They don't give you the initial unit. Find the acceleration when the velocity is 0. So first we need to even find the acceleration formula to begin with, right? So to find the acceleration formula, you take the derivative of the velocity formula. So it's just the second derivative of the initial position. So what would be the derivative of the velocity here?
2.
Just 2. So does it matter when they want us to find the velocity for?
Yeah, with t is 0.
Well, it doesn't matter because is the acceleration ever going to be different on this equation?
No,
No, there's no variable, right? There's no t left, right? So no matter where we talk about on this entire function, the acceleration is always 2. Do you see what I'm saying? It doesn't matter what spot I'm indicating. Okay. Next one says a particle moves along a vertical line. So its position at any time where t is greater than 0 is given by, where s is the measure in centimeters and t is the measure in seconds. So it says find the displacement during the first 6 seconds. So how you find displacement is displacement. You plug in whatever amount of time right here into the function. So you're going to plug in 6. So you're just going to plug 6 in here. And when you do that, you're actually going to get 8. So you can do that on your own if you want to plug it all in. And I just did it in the calculator. It's easier. So I just plugged in 6, and I got 8. And then, of course, you're going to plug in the initial time as well. So this is the final time. The initial time, of course, is 0, because you got to start somewhere, right? So if I plug in 0 here, what am I going to get when I plug in 0? Negative 4. Now, displacement is final minus initial, right? So it's going to be 8 minus a negative 4. which is going to be 12. So your displacement is 12 centimeters.
We did this in physics.
Yeah.
Oh yeah, you're definitely going to see stuff you do in physics in here. The next one says find the average velocity during the first 6 seconds. So average velocity is displacement over time, right? So displacement is 12, we just found it over the first 6 seconds, and then time that's passed. So from 0 seconds to 6 seconds, how much time has passed? 6 seconds. So our average velocity is 2 centimeters per second. Not to be confused with regular instantaneous velocity. So it says find velocity function and the acceleration function. Remind me, how do I find the velocity function again? It's the derivative of the original position function. So when I go to take the derivative of this right here, this 3 is going to come out front, right? What is 3 times a third? 1. So I'm just left with t squared, right? This is going to become minus 6t, and then this is going to become plus 8. What's going to happen with the negative 4? Goes away. To find the acceleration, you're going to take the derivative of this function, which is going to be what?
2t minus 6.
2t minus 6. So that's the first derivative and then the second derivative. And then it says when is the particle at rest? So a particle's at rest when its velocity is 0. Okay, that's always how it works. That's basically the slope of the original function is flat. The tangent line is flat. Okay? So we need to set the velocity equal to 0. So I'm going to zoom in here so you can see a little better. So to find when the particle's at rest, I'm going to set the velocity function equal to 0. And then your goal is just to solve for time. So how could we solve for time in this particular scenario? What? You got to factor it, right?
Put the 8 to the other side.
No, we can't do it like that because it's a trinomial, right? So we're looking for factors of 8 that add up to,
-4 and 2.
yeah, -4 and -2, right? So that's going to be at 2 and at 4. So there's 2 instances where our particle is at rest, and these are both in seconds, okay? So let me explain a little bit about why this is possible. You're going to notice that this is a cubic function, right? With positive, odd, and behavior. So I don't know exactly what it looks like, but it's going to look something like this. I know it has 2 turning points because it's cubic. Each one of these turning points means that at those points, the tangent lines are with a slope of what? 0. Obviously, I didn't put them in the correct spots because we're at 2 and 4, but basically that means that we have 2 situations where our velocity is at 0, and that occurs where we change direction, okay? So that's the reasoning behind that, why there's 2 times that this happens. Okay. So next one says modeling vertical motion. A heavy rock is propelled straight up with a launch velocity, and it reaches a height of, so this is vertical motion or horizontal motion? Yeah, it's essentially vertical. Of course, it's representing vertical motion. This is your position function right here. They always got to give you that initial position function. And this is representing the position here. This is time, and this is height, okay? So that's what's happening in this graph here. So time versus height. It says, when does the rock reach its maximum height? Well, if you look at this picture here, you can tell that that happens right here. This is a quadratic function, so anybody remember back to Algebra 2, what do we call that point on the quadratic?
Vertex.
The vertex. So back in Algebra 2, if you wanted to find when the rock reaches maximum height, you would find the axis of symmetry. If you remember the formula, x equals negative b over 2a.
Oh, yeah.
No? Maybe? Then you would take that, you would plug it back into the function to get the maximum height, right? That's how you would have done it in Algebra 2. What you were doing then was basically taking the derivative without knowing how to take the derivative. So I'm going to explain to you how that kind of relates into what we're doing here. So when does the rock reach its maximum height? Well, that occurs when the velocity is equal to 0, always. Maximum height is going to occur when that velocity is equal to 0 when we're dealing with this type of function. So, we have to first find the velocity function. How can we find the velocity function?
Derivative.
Take the derivative of the position function. What is the derivative of this function?
Negative 32t.
Well, that's part of it.
Oh, plus 160.
Yeah. So 160 minus 32t. So we get here. So everybody understand how I got that?
Yes.
Okay. Now it says, when does the rock reach its maximum height? Well, we know that happens when the velocity is 0. Okay? So we're going to plug 0 in for velocity. And now you just got to solve for t. So I'm going to add 32 to both sides. I divide by
Add 32 to both sides?
32t.
Oh, okay.
So we get 5 seconds. So it says when does the maximum height occur. It doesn't ask what the maximum height is. It occurs at 5 seconds. Okay? So what you basically just did was any of the times you originally used to do this, you used to do negative b, that would have been this, negative 160 divided by 2 times a. See how we just did that, but without using algebra, we did it with calc, okay? So now it says, how high does the rock go? Well, we know that the highest point is going to happen at what time?
5 seconds.
So what can we do with that information?
Plug in 5 for t in the initial equation.
That's true. We can plug 5 in for t. Are we going to plug 5 in for t in the velocity or the position function?
Position.
Position. Why would we use the position function here instead of the velocity function?
Because that's like the actual function where how it's moving.
Yeah. So make sure you understand which function is going to give you the information you want. If I plug this into the velocity function, that's going to tell me the speed at that time. We don't care what the speed is at the time. We want to know the height. Height is a type of position. So you have to make sure you plug it into the function that's going to give us the information we want. That's going to be the height function or the position function. So I'm going to plug that in here. And that's going to give me 400. And that's going to be feet per second. So we kind of already knew that from the graph. You can see it's at 400, but
Per second?
yeah.
Just do feet. It's asking for.
Oh, yeah. Sorry, yeah. You're right. I know. Okay. Find the velocity when the height is at 256 feet. So if we look at the velocity formula, is there a place where we can plug in height in here? Yes or no?
Yeah.
T is time. Is there a place where...
Well, you put in the original formula.
Well, so the point is, we're trying to find velocity when they give us height. We don't have a formula that directly relays velocity to height, right? So we have to use an intermediate formula to get the time, to then use time to get the velocity. So what we have to do is, we first have to find time when that's the height. So we're going to take this formula right here and plug in the height. So sometimes you're going to have to use more than one formula to get what you need. So before I can use the velocity formula, I first have to find the time at which the height is at 256 feet. Okay? Having to use the formula that indicates height in corresponding to time. So now to solve this, I need to get it into standard form. So I'm going to add 16t over to the left, and I'm going to subtract 160t over. So I just repositioned it to get it into standard form. The reason I did that instead of subtracting 256 over is because I wanted to make my a term positive. You see that? So you could have done it either way. Now I want to see if there's a GCF I can factor out, which would be, I can actually take out a 16. So that's going to give me t squared minus 10t plus 16. And then what would I do from here? I'm going to see if this will factor. Negative 2 and what other one? 8. Negative 2 and negative 8. Those would both multiply to give me a positive 16, but would add up to a negative 10, right? Then what could I do with these amounts? Well, I should have kept it as t, but sometimes I just forget and I do x. Sorry about that. T equals 2 and t equals 8. These are both in seconds, right? So there's actually 2 times where we're at a height of 256. That's to be expected though, right?
Yeah, 'cause it's gotta go back down.
Yeah, because here we're at about 256, and then here we're at 256, because it goes to 256 as it goes up, and then as it comes back down, right? So there's actually 2 times where that occurs. So now that we know the time at which the height is at 256, how can we use that to find the velocity?
Plug in the V of t equals.
Yes, good. We gotta plug into the V of t formula. 160 minus 32 times 2. And then we're also going to plug in 8. I think it's 96.
96.
So the speed at 2 seconds is 96 feet per second. Well, the velocity, rather. And the velocity at 8 seconds is negative 96 feet per second. So notice that the answers are the same, but they're opposite sign. Why do you think that is?
One's going down.
One's going down, one's going up. So the speed is the same, right?
Yes.
The velocity is different because they're opposite direction. Make sense?
Would that be for every sort of equation that